here. We're continuing on chapter 4, kind of where we left off. All right. Okay, so we've been talking about sort of the atom and some properties of the atom. We talked about some experiments that led to sort of our understanding of the atom. Again, the atom basically found out to be pretty much empty space. Within that sort of empty space is where we have our electrons that are flying around, sort of again randomly moving about that area. Within sort of the center there of the atom, we have the nucleus. The nucleus is where we find our protons, which are positively charged particles, and also where we find our neutrons, which have no charge. The neutron, again, being the heaviest of all those particles, and the proton being pretty close to it. And again, that's why, again, the nucleus there is the most of the mass of the atom. Electron is significantly less massive than those two, about 1,800 times less heavy than a proton or electron, and they're flying about. With that, we started talking about some ways to figure out protons, electrons, neutrons. We could use the atomic number, which is found on the periodic table. The atomic number is the number that comes above the symbol there on the periodic table, as we talked about. So again, if we looked at, say, the carbon box there, which is 6 and 12.01. Number up there on top is our atomic number, which is our number of protons. Also, it will tell us the number of electrons if it is neutral. Remember that the definition, though, atomic number is just protons, but it will also give you that electron information. We also have the mass number, which is not found on the periodic table, and the mass number is our protons plus our neutrons. And we oftentimes will write the symbols like so: mass number up top left of the symbol, atomic number there, bottom left of the symbol. Remember that, if something does have a charge, it's the electrons that actually change. Protons don't change because, as we talked about, what basically determines what element you're dealing with is the protons. So if you change the protons, and by definition you change the atomic number up there, you are changing what the element is. So protons are very important. That atomic number is very important. And again, if you look at the periodic table, there's not a number that repeats. So every element has its own atomic number, and that's why we can identify it by its atomic number, or the number of protons. All right, so where we left off is right here. We're actually now going to talk about this bottom number. And remember, again, the bottom number actually is not the mass number like I mentioned before. This is what is referred to as the atomic mass. And the atomic mass is, as we'll talk about, not, again, the same as the mass number. So a reminder that if the mass number you're looking for the atomic number, you're looking for the number of protons, electrons, neutrons, all those things should be whole numbers, positive whole numbers. And again, if you look at all these sort of bottom numbers on the periodic table, they're definitely not whole numbers. So again, they are really the atomic mass. So let's talk about the atomic mass and sort of what it is. The atomic mass, one of the fundamental properties of an atom, obviously, is its mass. It is related really to all the subatomic particles that are present, electrons, protons, and neutrons. But obviously, something like an atom is extremely small, so you can't really just pick it up and put it on like a scale and get the mass of it. So typically what in science they do oftentimes is they decide, well, we can't sort of maybe directly measure it. So let's pick something to use as a standard. So they did that for the atomic mass. They chose really an isotope of carbon to act as basically the standard. So they chose this carbon-12 isotope, carbon-12, 12 being the mass number, atomic number obviously being 6. And it had really 6 protons, 6 neutrons, but it had a mass of exactly 12 AMU, what is referred to. AMU is an atomic mass unit. It's a unit of mass. And they used this guy as basically the standard, and they basically compared other elements to it. So, for example, they looked at hydrogen, and they said, hey, hydrogen, it's only about 8.4% as massive as this carbon-12 isotope. So what they essentially did was they took 8.4%, which is what this number is. We need to divide by 100 or move the decimal point 2 places to the left, times it by 12, which is the atomic mass of our carbon-12 isotope, our standard guy, and they come up with this value of 1.008. So if you look at the periodic table and you look under hydrogen, you will find a number very similar to that, 1.008. So similar sort of calculations were done for things like oxygen, which is 16, iron, which is 5585. The atomic masses, again, are those numbers that are underneath the symbol on the periodic table. And again, related to really the number of protons, electrons, and neutrons. So you may say to yourself, well, if they chose the carbon-12 isotope as the standard and it had a mass of 12, you know, why, when I take a peek at the periodic table there for carbon, it doesn't show 12, but it actually shows 12.01 as sort of the atomic mass. So what's the deal? I mean, I thought they used, again, the carbon-12 as sort of our standard to do that. Well, what we're really seeing when we look at the atomic mass on the periodic table is what is really referred to as the average atomic mass, although most people don't use the word average. And what it really is the average atomic mass of all the naturally occurring isotopes. For that element. So if you remember, an isotope is the same element, but it has a different mass because it has a different number of neutrons that are present. And that's, again, what makes something an isotope. So when we look at something like carbon, for example, there's the carbon-12 isotope that's got a mass of like 12. There's also naturally occurring carbon-13 isotope that has a mass of about 13. Now, when we have naturally occurring isotopes, they sometimes appear in different percentages. So what I mean by that is sometimes referred to as relative abundance or percent abundance. And that's basically the percentage at which we find these isotopes sort of naturally occurring. Obviously, if they're all the naturally occurring isotopes, it should end up with a relative abundance of 100%, right? And that's how we get all those values. So let's take a look specifically here at carbon. And if we have carbon, there is sort of a formula that we could follow to, scratch this out for now. There's a formula that we could follow really to calculate the atomic mass. So if you wanted to calculate the atomic mass, you basically would take the percent abundance of the isotope, times it by the atomic mass of the first isotope. Then you would actually add it, not multiply, but actually add it to the percentage of the second isotope that's present. And you would times it by the atomic mass of the second isotope. And then you would add it to, if there was a third, do the same sort of procedure. So to take the percentage times the abundance plus the percentage times the abundance, and when you add it all together, then you will get basically the atomic mass of that element. So let's take a look here at carbon. So here's our carbon-12 isotope. It has a mass of 12 AMU. It occurs about 98.9% of the time. This is our carbon-13 isotope, which has a mass of about 13. And it occurs, as you can see here, about 1.11% of the time. I can feel pretty safe about my calculation here because when I add up both of those percentages, I end up with about 100%, right? Which means I definitely have hit all of the naturally occurring isotopes here. So if we were to do this calculation to figure out the atomic mass, we would take our first isotope, which would be this guy. We would take the percentage and convert it into a decimal. That means move the decimal point 2 places to the left, times it by the atomic mass of our first isotope. Then we would add it to the second isotope here. Also want to convert the percentage into a usable number. And if you don't want to move the decimal point, you essentially can divide the percentage by 100% and times it by our 13.003 AMU. And if we do all that good stuff there and actually punch the right numbers, let's see here, 12 plus basically 0.0111 times 13.003, we end up with something like 12.0 2 AMU. I get, it's slightly off. They did some rounding, I'm sure, but pretty darn close to what we do see there on the periodic table. So when we look at those numbers underneath the symbol, they are really the naturally occurring isotopes of all the elements that are present, and that's what we see. Again, we don't usually sort of refer to it as average atomic mass, but we do, kind of call it average, call it just the atomic mass. Any questions on how to calculate that? Obviously, if you were missing a percentage or something like that, you would think about 100% being all of it, and you can figure out any type of missing percentage. So why don't you take a second here and figure out the atomic mass here of bromine that has 2 stable isotopes, bromine 79 and 81. Those are the percent abundances and the atomic masses for each of them. So see what you come up with, and then we'll talk. All right, I see some answers coming in here, which is good. Let's take a looky here and see. So again, if we sort of follow our pattern here, we have a number of isotopes. So we want to take the atomic mass, again, would be the percentage of our first guy. And again, you want to take a quick look at both of those percentages, add them together. It's approximately 100%. Again, that means we're not missing anybody along the way. So we'll take our first bromine 79 there, and we'll do the conversion into a decimal, divide by 100, times it by our mass of that first isotope. We then would take the percentage of the second guy. Also, again, you could divide it by 100 or just move the decimal point, times it by our 80.92 AMU. And it looks like I feel like the overwhelming response there was D, so I would tend to probably agree with you. Let's see. It is 79.92 AMU, and it looked like that's what people were putting, and it is D. Very good. Any questions on that particular one there? Okay, questions on how to calculate atomic mass. Again, if you had more than 2, you would just continue this sort of pattern and add at the end here, the same sort of process. And again, you always want in these sort of problems, just make sure you're not missing a percentage anywhere and make sure that all the percentages do add up to about 100%. Any questions on that there? Okay, then let us talk about the periodic table. So obviously this is a periodic table. It is an arrangement of the elements. We're going to talk about different parts of the periodic table here. First off, let's talk about A group, or if you're really old like me, a family. Not too many people use families anymore. Most people use groups. We here in most chemistry classes, and this periodic table is pretty good. A lot of periodic tables, you'll see a couple different numbering. So over the A numbering here, you also sometimes see the B numbering here. Sometimes you'll see like no letters next to it as well. But for the most part, we use the A numbering, which is sometimes referred to as the representative numbering for groups. Groups go up and down. So this way on the periodic table, it's a group. So when we talk about group 1, it is right here. Most people don't call it 1A, but it is 1A. And by the way, even though on most periodic tables, hydrogen is sitting right there, group 1 actually starts with lithium. So hydrogen is not part of group 1. It is, even though it's on most periodic tables there, lithium is the first member of group number 1. Right next door is group number 2. Again, going down, we skip all this middle part here, and we come over here. This is group number 3. Again, going down where boron is. Group 4, carbon and down. Group 5, nitrogen and down. Group 6, oxygen and down. And 7, fluorine and down. And group, not 18, 8. That's what most people call it. Helium and down. So those are groups going up and down on the periodic table. That's not to be confused with a period, which goes left to right on the periodic table. So a period heads this way on the periodic table. And they do have numbering as well. 1 through 7 is our period numbering. And obviously period 1 goes this way, period 2 this way, period 3 this way, 4 this way, and so forth. So groups up and down, periods left to right on the periodic table. We've already talked about the number that comes up there on top. That's our atomic number, which, as we talked about before, is our number of protons. Again, important number because it does not repeat as you look at it. And again, every single element has its own unique atomic number. Any questions on that there? Yeah, truthfully, I guess the way to how to put this, it doesn't matter, but it might, in the sense that, and the question obviously is, is there really a difference between these two? And there's not, but for this class, for the most part, and probably any chemistry class that you take, we do use that A numbering. So probably 99 times out of 100, nobody would call this 17. They would call it either group 7, or sometimes people will call it 7A. So most of the time people will just call it group 7, and very, very rarely will you probably ever hear anybody call it group 17 in that sense. Is it not? Is there a difference? There's really not, but for us and in here, probably for the lab as well, you would probably want to stick with this A numbering as to how you would sort of identify those groups. Other questions on that? Okay. Now, the periodic table is broken off into several sort of categories. We're going to talk about all that, so just be patient. We'll get there to all those questions, I think. So the periodic table is basically broken off into 3 different categories. There's metals, nonmetals, and metalloids. On most periodic tables, you can see a staircase like we have here, a staircase. And to the left of the staircase, including those 2 rows at the bottom, those are all metals. Metals are good conductors of electricity. They're also usually room temperature. They're usually solids. The one exception for metals is mercury, which is ballpark right about here. That's actually a liquid at room temperature. Pretty much all other metals are going to be solids. Up and to the right here of the staircase are nonmetals. Nonmetals pretty much have the opposite sort of properties. They are dull and brittle. They're insulators. But what nonmetals have is a very different sort of physical properties. Some of them are gases, like our nitrogen, our chlorine, our fluorine, our bromine, our oxygen, our hydrogen, and who am I missing there? Iodine, and our iodine. Those are the guys that comes as twos, but nitrogen, oxygen, chlorine are gases. Bromine is a liquid. Some are solids. And that is why if you look right here at this guy is hydrogen. And you can see by the color, hydrogen is actually a nonmetal, even though it's hanging out over here on every periodic table you ever see. Years ago, they actually used to put hydrogen on both sides as well. So if you find an older periodic table, you might actually see hydrogen on the right-hand side and the left-hand side. More newer periodic tables don't do that too much anymore. But hydrogen is actually a nonmetal, and that's why here, which is lithium, is a metal, and that's why lithium and not hydrogen is actually the first member of group 1 in that particular case. Here in sort of our staircase area here, some books will include boron. I don't know if yours does or not. I'm trying to remember, but some books will include boron, some books won't. These are what are referred to as metalloids. They're also sometimes called semi-metals, and that's because they really have properties that fall on both sides. So the same element has properties that are very much like metal properties, and the same element will have properties that are very similar to non-metals, which makes sense. We're kind of going from metals into non-metals here, and these guys kind of fall on both sides in terms of their properties. Now, there are some groups that have special names. So starting right here at group number 1, those are the alkali metals, and you do need to know these names. So that's the alkali metals. Again, starting with lithium, hydrogen not part of that because it's a non-metal. Going right next door, that's our alkaline earth metals in group number 2. Alkaline, that really means basic. And a lot of bases like sodium hydroxide, potassium hydroxide are found there in group 1 and group 2 is where they sort of come from. We skip the middle section here, heading over to group 7. Group 7 is the halogens. That's our fluorine, chlorine, bromine, iodine. Those are a lot of our guys that come naturally as twos when they're all by themselves. And over here in group number 8 is our noble gases. Noble gases are sometimes called rare gases if you're old like me, but they're sometimes called rare gases. Not too many people call it that much anymore, but noble gases. Noble gases are what are referred to as being chemically inert, which means they are not very reactive with anybody. They are just perfectly stable by themselves. And as we'll talk about with bonding and everything, that is why the basis of bonding is for everybody really to end up like our noble gases. And we'll talk about that as we continue on, but that's sort of the basis of all of it. Couple of other things. We have 2 rows down here, which are set aside because make the periodic table too big. If you follow the atomic number here, we got 55, 56, 57, and 72. Here's our 58 right there. That whole row goes right there, technically speaking. If you follow below it, 88, 89, 104. Here's our 90. Our 90 technically goes right there as well. Those are called the Lanthanides and Actinides because those are the 2 elements they follow on the periodic table. I've never seen a periodic table with those 2 rows in the proper place other than one time, and it was on a wall because it hadn't needed the whole wall to fit everybody in because it's spread out so much. So we usually see those guys on the bottom. In addition, there's another big group here which are referred to as the transition metals, and that is between group number 2 and group number 3 on the periodic table all the way through here. So all these guys really in this area here, these are all transition metals between group number 2 and group number 3 there. So you do need to know where the alkali metals are, the alkaline earth metals, where the halogens are, where the noble gases are. You do need to know how to properly number everybody in terms of group number, and that proper numbering is the A numbering. So that A numbering is what you need to do, where again, group 1, group 2, skip, group 3, group 4, group 5, group 6, group 7, and group 8. You need to know where the transition metals are, which are between here. And obviously you need to know where the lanthanides and actinides are as well. Any questions on the periodic table? Obviously you need to know which way a period goes as well, right? Okay. All right, so now we talked about the periodic table. We're going to talk about electrons and sort of where electrons are in the atom, electron configuration, and all that good stuff. So first off, though, a lot of what we're talking about, and we don't get into a tremendous amount of detail, but a lot of what we talk about is atoms, they have electrons. And if electrons are represented by an arrow, there are electrons on different energy levels. And sometimes what happens when we excite an atom, either heat it up, run electrical current through it, these electrons in a lower energy level will get excited up to a higher energy level. But what happens when that occurs is, for the most part, things don't like to be in higher energy. So they will try to work their way back down in terms of energy. But there's a conservation of energy that occurs. So while they're doing that, they will give off energy in the form of light. And if that energy that gives off has a wavelength that corresponds to visible light, we'll actually be able to see color. That's where we see colors and stuff like that. There is a relationship between wavelength and energy, and a wave is just something like this. And the wavelength, which is sometimes, oops, as I hit the wrong thing there, get that out of the way. The wavelength is sometimes abbreviated by lambda. That stands for wavelength. And if we have a really long wavelength, it has a very low, what is referred to as frequency, which is how often something passes a point in a given second. And it has a low energy associated with that. And that's different than if we have a much, we'll go this way, much smaller wavelength, like so. Wavelength here is definitely much smaller. When we have a smaller wavelength, we usually have a much higher frequency. And what that results in is higher energy. So this is what is referred to as electromagnetic spectrum. And here's the wavelength. And this is long wavelength over here. I'll spit that out. And over here, 10 to the minus 11 is a small wavelength. And we see higher energy on this side, lower energy on this side. So over here, for example, we have like radio waves, right? Like we listen to the radio. We also then have some television in there. As we go to the right, the wavelength is getting smaller, more energy. We have like microwaves. So you can put your pizza in the microwave, speeds up those water molecules really fast, cooks up the pizza in 3 minutes, you're good to go. Infrared is sort of where we feel heat, again, getting smaller in our wavelength, higher in our energy. Over here is what is sometimes referred to as the visible part of the spectrum. So this is the visible part of the spectrum. This is where we see colors that Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, and violet. Probably missed where those letters go, but you get the idea. And actually the colors, there's different energies associated with color. As we can see, 700 nanometers is a much larger number than 400 nanometers, which is where our purple or violet is. So actually a purple wave is actually more energy than a red wave that we would see. So when we see red light, it's less energy than, say, purple light. So less energy on this side. Then we get into things like ultraviolet. When we go past the visible part of the spectrum, ultraviolet is getting more energy. That's why we put like sunblock on, so we don't get too sunburned from damage from UV light. X-rays, even more energy, smaller wavelength. Why they put the lead vest on you and then they leave the room when they shoot the X-ray usually, right? Because it gives off a lot of energy. And lastly, here we have gamma rays. Gamma rays are really just pure radiation, just very, very high in energy. So as we go left to right on this picture, lower energy to higher energy, longer wavelength to shorter wavelength, and in terms of frequency, lower frequency to higher frequency as we go left to right here. You do need to know the order here. You don't need to know any like specific numbers, but you need to be able to put things in order for like, put things in order of like shortest wavelength to highest, lower energy to highest, and so forth. So if you're given some of those guys like radio waves, infrared, UV, visible part of the spectrum, you need to be able to put them in order. Any questions on that? Again, you don't need to know any specific breakout. You also need to know in terms of the colors as well, that order as well, in terms of the visible part of the spectrum, the actual colors. Here's just another one of what we just saw, basically, just going the opposite direction. This is our longer wavelength on this one, shorter wavelength on that one, but we see the same trend. So let's talk a little bit about that then. Identify the form of electromagnetic radiation in each pair that has the greater energies. So remember, when we're looking at this guy, this is longer wavelength, shorter wavelength. So blue should have more energy. Ultraviolet or infrared there. I'll spit that out there. So ultraviolet's here, infrared's here. Ultraviolet has the smaller wavelength, which means it should be more energy in that particular case. So it should be our UV. And then X-rays obviously does. We can look at the chart, but just from normal practice, usually, right? Our microwave versus our X-rays, we don't usually put a lead vest on there when we're microwaving. Maybe we should, but we don't. And our UV, our X-rays, we definitely do. So X-rays, again, being shorter. So again, that relationship, shorter wavelength, higher frequency, higher energy. So shorter the wavelength, higher frequency, higher energy. And opposite is true, longer wavelength, lower frequency, and lower energy. Any questions on that particular one there? So how this relates is, as I was mentioning before, what we typically will see is these electrons, when they do gain energy in these atoms, we do see these electrons sort of transition, like I said, up to higher energy levels. And as they work their way back down, they are going to give off that energy of light. And like I said, depending on where that energy of light falls in terms of its wavelength, if it does fall in this sort of visible part of the spectrum, we'll see color. If it falls outside of it in the infrared, we might feel heat or something like that. But one thing that happens when we sort of excite an element by this, either in a flame test or an electrical discharge tube, and we run that light through a prism which separates out all the light. One thing that elements usually will do is it gives its own unique, what is sometimes referred to as an atomic spectrum, or sometimes referred to as an emission spectrum. And this is what is referred to really as a line spectrum, because just like the name implies, we see distinct lines that occur at specific wavelengths. The interesting thing about elements and their emission spectrum is every single element has its own unique emission spectrum. So every element has its own unique emission spectrum, like we just talked about, which means if you look at sort of a light through a prism that's being given off, you'll be able to see these distinct lines that occur and go, oh, I got this colored line at this wavelength, this one, this one, this one at this wavelength. Oh, that's the emission spectrum for hydrogen. Or, maybe I only see 3 lines at different spots in different colors. oh, that's maybe neon's sort of emission spectrum. So you could actually identify which one you're talking about based on the actual colors that you see when you look at them. So when these electrons really do transition from one energy level to the next, we sometimes refer to these as energy levels as N. And N is the principal quantum number, which is a very fancy word for basically the energy level. So within an atom, there's these different energy levels where electrons can be found out from the nucleus. So we got the nucleus there. There's these different energy levels that will be found. They could have values of basically N can equal 1 through 7. And if N equals 1, that is what is referred to as the ground state. That is the lowest in energy and closest to the nucleus. Anything above that, like N equals 2 through 7, those are what are sometimes referred to as excited states. They are higher in energy. So when we look at like N equals 1, there's a certain amount of electrons that could be there. N equals 2, N equals 3, and so forth. Energy increasing, and distance from the nucleus increasing as we go from one energy level basically to the next. So an important part about these energy levels is they're basically what are referred to as being quantized, which is also a fancy word for basically meaning electrons will either gain or lose energy in whole packets of energy, which was sometimes referred to. And really what that means is you could kind of think about it like a staircase, for example. They use a bookshelf, I guess. If we were to walk stairs, right, we would find ourselves maybe on this step, or we would have enough energy to get to this step, right? The next step. Some people have enough energy to go from one step to like the second step. Some people have enough energy to go from like the first step to the third step. And not too many people could go from 1 to 4, I don't think. But, you know, you either have enough energy really to go from one sort of step to the next. And if you were walking the stairs, you wouldn't find yourself go, oh, I got to this step. I'm going to go to the next step. No, I'm tired. I'm just going to kind of rest in between steps. You would fall, right? So typically we don't see that happen. And that's the idea behind quantized energy levels. We either have an electron on the N equals 1 level, or N equals 2, N equals 3. And if that electron is not on the first energy level, for example, it will definitely gain enough energy to make it all the way up to the whatever level it's going to end up at. So maybe the third level. It won't find itself like halfway between levels or anything like that. It will either gain enough energy to get there, or it will lose enough energy to come back down energy levels. Again, we won't find electrons hanging out like, I don't really want to get to the 4th energy level, but I don't want to stay on the 3rd energy level. I'm just kind of hang out in this sort of energy in between. So that's what it means by quantized energy. They have enough energy to either make it all the way up to one level, and if they're coming back down, they have enough energy to come back down to an energy level. It may be one energy level at a time. Certain electrons could go multiple energy levels at a time, but definitely they will never find themselves sort of in between the process. Any questions on that? Now, as these guys are basically changing energy levels, in terms of energy, there's two things happening in terms of the atom. If my electron is starting out at a lower energy level and ending at a higher energy level, up to here, it has now just absorbed energy to do that. It needs to absorb a certain amount of energy to do that. That's sometimes referred to as being endothermic, like we talked about energy. And energy has to be put into the atom to excite those electrons to the top. But if my electron decides I want to come back down, which it most likely will, because lower states of energy is always more stable. If my electron started at the third energy level and wanted to come back down to the first energy level, it would come back down. But in order to do that, as I mentioned before, it has to give off that energy in the form of a wave. And this is what is referred to as the energy being released or emitted. And that's also like an exothermic process in terms of energy. It would be negative, and that's what we see here. This electron here gains enough energy to make it all the way up here. Then he decides he wants to come back down. He gives off that energy in the form of the light, and that light happened to correspond to the wavelength for red light in the visible part of the spectrum. Thus, we would see red light. Same thing is happening on the other one here. Electron gets excited to the top, comes back down, gives off energy in the form of green light. Let's look at the difference in transitions here. The energy level between here and here, much smaller than between here and here. Here we have a red light coming off, which is lower in energy and longer in wavelength. Here we have a green light on the bottom coming off, larger in energy, smaller in the wavelength. Again, you can see the wavelength here is much smaller than it is here. Any questions on that? This is basically like when we see fireworks, right? They launch fireworks up in the air, they explode them. When they explode them, all the elements that are in the fireworks gain a lot of energy. All their electrons also gain a lot of energy and work their ways up to these higher energy levels. But eventually they will start working their way back down. And depending on what elements are present, we see pretty colors, right? When we see fireworks explode, maybe we see red, we see blue, we see green in fireworks. And it's really those specific elements that will have those transitions that occur that correspond to those colors. So that's sort of what's happening when you kind of see fireworks. Again, if you ever boiled water to make pasta and the water over boils and the water hits the flame, you'll sometimes see it like turn maybe yellow really quick or orangey yellow, and that's really because there's sodium in your water a lot of times, salt, and it's basically the sodium electrons being excited and emitting those colors that you see when you boil water. Any questions on that? So let's talk about this. An electron moves from the first energy level to the third. We're going from 1 to 3, like my example. In order to do that, it needs to absorb energy to do that, right? It needs to gain energy to go from lower energy to higher. An electron falls from the third to the second. So my electron starting here, coming back down. When it comes back down, it needs to emit that energy or release that energy. An electron moves within the third energy level. So if it's just hanging out here in the third energy level to third energy level, same energy level, not much happening. So really no change occurring at that point. Any questions on that? So within an atom, we have these different energy levels. And within these different energy levels, like I said, there's sort of the ground state and these excited states. And that's where we find electrons. And where do we find electrons? As I mentioned before, electrons really don't travel in these pretty circles. Sometimes a guy by the name of Bohr had this sort of planetary model where you have a nucleus, you have these orbits in which electrons are pretty much kind of going in a circle, and it really doesn't happen that way. And it's a much harder chance of knowing where an electron is, how it's moving at any given point in time. So what we have done is we move away from this idea of orbits where we find electrons in the atom. And the best we could do is something basically known as like probability of finding an electron. we still don't know, and it's sometimes referred to as Heisenberg's uncertainty principle. We still don't know how the electron got there, where it's traveling, but we do know it's not going in pretty circles. It is traveling, as I might have mentioned, pretty randomly about the nucleus. But where do we kind of find them? So they moved away from that to more of a theoretical model, which are referred to as orbitals, or sometimes referred to as atomic orbitals. And atomic orbitals are really theoretical maps in an atom where we could find electrons. There are a few different types. There's s orbitals, there's p orbitals, there's d orbitals, and there's f orbitals. One important aspect is any orbital, any individual orbital can hold a maximum of 2 electrons only. So it can only hold a maximum of 2 electrons only. So if we want to represent an orbital by this little line, we could only hold a maximum of 2 electrons if each arrow represents an electron. Let's say this is a 1s orbital. It would only be able to hold basically 2 electrons. So what do these orbitals look like? Here are some pictures of these orbitals. S orbitals are basically a sphere, a circle. S orbitals start at the first energy level. They start at n equals 1 is where we first see s orbitals. There's only one type or number. So one s orbital, no matter what energy level you're at. These are p orbitals. P orbitals look like figure eights, and they start at the n equals 2 levels where we first start to see p orbitals appear. There's actually 3 different p orbitals. There's a px orbital, a py orbital, and a pz orbital. They're on different, sort of like in math, there's an x, y, and z, very badly drawn, axis in 3-dimensional space. So you got one coming this way, you got one hanging out this way, and very badly drawn, you got one coming that way on like the x, y, and z axis in sort of a coordinate plane there. D orbitals start on the 3rd energy level. That's where we first start to see them. And there are 5 different d orbitals. And f orbitals start to appear on the 4th energy level. And there are 7 different d orbitals. That means that if I max out number of electrons, s orbitals can only hold a maximum of 2. Because there is we'll talk about valence electrons too in just a bit as well. So we can max out with 2 electrons in our s orbitals. Our p orbitals, because there are 3 different p orbitals, our s orbital here, again, could have 2 electrons. There's the px, the py, and the pz. We can put an electron in each of these orbitals, 2 of them actually, and that is 2, 4, 6 total electrons if we max out all 3 of those p orbitals. Because there's 5 different d orbitals, 2, 3, 4, 5, we can put 2 electrons into each of them. By the way, they go in one at a time, just like this, and then they come back in the other way and fill up. That's how they go in. And we can see we can max out at 10 electrons. And there are 7 different f orbitals, which each one could hold 2 electrons. Again, they do go in one at a time. And then they come back and pair up in terms of how those electrons actually go in. And that would be a grand total of 14 electrons. So these are where we theoretically find electrons in the atom. They are orbitals, and they are sometimes referred to as orbitals. And all of these here, though, together, That is a subshell or sublevel. That is a D subshell or sublevel. And that is an F subshell or sublevel. And we'll talk about that here in just a second. Any questions on that so far? So these are where we find basically the electrons in an atom in these sort of theoretical sort of orbitals. We assume the nucleus, for example, in a p is about there. Nucleus is about there in an s orbital. This sort of darker blue sort of area is a higher probability of finding electrons. And kind of the lighter areas, it's less of a probability of finding an electron. Here's our different px, py, and pz, just like I drew it, sort of. Again, basically different locations in three-dimensional space. So there's actually an order at which we find these orbitals and how electrons go in. So when we only have one electron, for example, this is what it all looks like. And this is our n equals 1 level, or n equals 2 level, or n equals 3 level, or n equals 4 level. And a couple of things, as I was just mentioning, that we should talk about some terminology. Let's say I ask, how many electrons would fill the n equals 2 level or shell. So take a second and think about what you think that might be. So when we talk about a level or a shell, we are talking about every single orbital that would be found on that particular level, which is my n equals 2 level. Each of these lines represents an individual orbital, which means I could put 1 electron here, 2 electrons here. That is full. They would go in, like I said, one at a time here in the upwards direction, and then the electrons would come back and pair off, which means if we count it, that is 2, 4, 6, and 8 electrons would be put in there. So it would only be 8 electrons if I filled up the n equals 2 shell or level. So again, shell or level, we're talking about the entire, every single individual orbital that is found there. Now, if I ask how many electrons to fill the 3p subshell or sublevel, sometimes called, take a second and think about what you think the answer would be to that one. So when I talk about the subshell or sublevel 3p, I'm specifically talking about all 3 of these p orbitals. That's our px, our py, and our pz orbital. Again, 1 electron, 2 electrons, 3 electrons, 4 electrons, 5 electrons, 6 electrons, if I fill the entire 3p subshell. What does a 3p subshell stand for? 3 means it's on the 3rd energy level. P means it's the type of orbital we're dealing with. And again, the subshell would be all of those guys together. And lastly, if I ask something like how many electrons in a 4D orbital, what would the answer be on that one? Okay, I see a lot of answers coming in. I see 10. Okay, so 4D is definitely over here, but I did not say the 4D subshell, which would encompass all of those. I said a 4D orbital. So any orbital by itself could only hold 2 electrons. I may be talking about this orbital, could be talking about the one next to it, could be talking about the one next to it, could be talking about the one next to it, or the one next to it. So if it asks just about an individual orbital, the answer is always 2. If I said how much in the 4D subshell or sublevel, that would be 10, because then we're talking about everybody that is present. That's sometimes a trick question that's asked, especially in lab. They sometimes ask that question and stuff like that. So again, any orbital, no matter what energy level, if we're talking about just one individual orbital by itself, can only hold a maximum of 2 electrons. Any questions on that there? It depends what you would, it depends what the question is asked. So if I asked, you know, how many electrons in a 4f orbital, a 4f orbital, it would still be 2 electrons. If you did a 4f subshell, it would be all of them together. Since there's 7, it would be 14 electrons. So again, that little difference there is an important meaning when you're asked about that. Now, maybe you might want to know like how many electrons are like in the entire n equals 4 level, which would include everybody there, but maybe you don't want to draw it. So there's a quick way you could kind of do this calculation here. You could take 2 times n squared, n being the principal quantum number. So for example, the one we did, which was 2. 2 times 2 squared gives me 2 times 4, which gives me 8 electrons total if I maxed it out. If I did the third energy level, which would be everybody on the third energy level, it would be 2 times 3 squared. 3 squared is 9. 9 times 2 is 18 electrons if you filled up everybody. 2, 4, 6, 8, 10, 12, 14, 16, and 18 electrons if you filled everybody up. So this is a good little kind of quick way if you're trying to calculate, you know, the maximum number of electrons to fill up a particular level or shell. You could do that. Any questions on that there? Okay, so when we're dealing with just hydrogen by itself, these orbitals are nice and even with each other. And what I mean by that is all the guys on the second energy level, they're all on the second. All the orbitals on the third, they're all perfectly even with energy. But what happens when we have more than one electron is we get electrons near electrons, and they really don't want to be there. So there's a lot of changing that occurs in the energy of the orbitals. And you can kind of see it here if we go to the next slide. Kind of the difference there. They're all equal, then they all sort of shift. So what is this effect? Well, electrons always go in lowest energy first. So when we would fill it up, we would go 1 electron there, 2, that would be filled. Next lowest would be the 2s orbital. That would be filled. Next lowest would be our p orbital, 2p. We would fill that one up completely. We then would go to our 3s, which is the lowest in energy. Then our 3p, again, one at a time, coming back and filling up everybody. And now here's where the difference is. 3p, you would think, well, 3d should come next, but it actually doesn't. The next lowest energy is actually the 4s. So it would get the electrons first, followed by the D. And that pattern repeats. We go from the P to the S to the D. So that pattern does repeat. So electrons continuously fill until they're done, until they've used, basically put in all their electrons that they need. So there is a nice little way that you can kind of come up with this. This is the order at which we kind of do the electrons. You could actually make it yourself. Basically, you just go 1 through 7, and you go 1s, 2s, 3s, 4s, 5s, 6s, 7s. Remember that p orbitals don't start till the second energy level, so you start at 2, and 3p, 4p, 5p, 6p, 7p. Remember, d orbitals don't start to the third energy level, so you go to 3, 4, 5, and 6. F's don't start until the fourth. And you can recreate this pretty quickly. We always start at the top, and we zigzag back and forth until we fill it. So zigzag, zigzag. If you know this order, and you know what we talked about, that if you max out in terms of electrons, an S maxes out at 2, P subshell maxes out at 6, D subshell maxes out at 10, F subshell maxes out at 14, you will be able to write any electron configuration you need to write. Any questions on that? So those two things are really important. You also, like I said, can recreate it for yourself fairly quickly. So let's talk.
Question.
Yeah.
Does the valence electrons, does that always equal the group number?
It does.
That's what I'm trying to find out, that my answers, it's not equaling the group number.
We'll get to it in just a second, I promise.
Okay, thank you.
Or if not, I'll definitely answer before we were done here for lecture.
Okay.
Yep. Other questions on that? Okay. And it'll come apparent here in just a second as we start writing some of these electron configurations. We'll talk about as we do that as well. So let's talk about actually writing electron configuration. Electron configuration basically tells us how the electrons are distributed among those atomic orbitals. And remember that if an atom is neutral, that means it needs to have the same amount of positive charges as negative charges. That means in terms of an atom, same protons as electrons. So if we know the atomic number, we'll also know the electrons in a neutral element. So let us start with hydrogen here as our first one. So if we go to the periodic table and we, actually, let me do it like this here real quick. Let me just make that real quick so we can kind of see it again. So again, if I just want to make my little chart like I had, so I'm not flipping back and forth. P, 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 5P, 6P, 7P, and 3D, 4D, 5D, 6D, 4F, 5F. Okay, so again, we always start here. So coming this way is where we always start. So let us take a look then at hydrogen. Hydrogen's atomic number is 1, which means it has 1 valence electron. So we would start at the top there, and we would go this way, coming through this way, takes us to 1s1. So 1s1 is how we basically determine electron configuration, or say it. The first one is the principal quantum number, is that N number. It's basically the energy level. The S is the orbital it's in, our subshell. In this case, is an orbital. And the 1 up on top, which is how it should be written, is the number of electrons that are there. Now, where I'm showing you with this electron configuration is the way you should write electron configuration. I know your book just uses numbers. I've never seen anybody other than her use numbers, like, hey, it's 2, 8, 6, like we're cheering for somebody. Don't do it. Don't write electron configuration like that unless somebody specifically tells you to do it. For lecture, for sure, do it this way. I'm assuming for lab as well. Any questions on that? We can also see that we can continue on to, let's take a look at helium, which is next. Helium is number 2 on the periodic table, which means, again, we would start back here. We would come this way. Again, we're here. So that's going to be 1s2 for the configuration for helium. Again, the first one represents the energy level. The S is where the electrons are, and that's how many electrons are in that orbital. And in this particular case, because we know an s orbital can only hold 2 electrons, we cannot put any more in there. So why don't we continue on to lithium, which is number 3. Again, it has 3 electrons, so we're going to start back up here again. So the first part of it is 1s2. Again, because that's an s orbital, it cannot hold any more electrons. That means we need to zigzag back around and come down this way. And the next electrons would end up in the 2s orbital, and we'd only need to put 1 here. Now, in this particular case, we have a grand total, if we count the top, 2 electrons and 1 electron, which is a grand total of 3 electrons. No commas, no dashes, no capital letters. This is the way electron configuration should look. 1s2, 2s1. Any questions on that? So since you asked that question, why don't we talk a little bit about it when we have this one? What does this really mean? So when we look at these first numbers, these are the energy levels. And what that means is for lithium, on the very first energy level, it has 2 electrons. When we go to the second energy level, it has 1 electron. For lithium, that 1 electron is its valence electron. Valence electrons are the highest in energy level electrons. And for the lithium, it has 1 that is on the second energy level. These ones that are closer to the nucleus, these are what are referred to as core electrons. They are closer to the nucleus. They are held tighter. They are not involved in bonding. If you look at lithium on the periodic table, it is in group number 1. So it does match the group number here. As was asked before, the group number does equal the number of valence electrons. If we look at helium, for example, right? Helium here only has electrons on the first energy level, which means all 2 of these are its valence electrons. So helium will not match the group number because it only has a total of 2 electrons, but these are all its valence electrons for helium. And that's why helium is a little bit different because of that. It is part of group 8, but it only has a maximum of 2 electrons, so it cannot have 8 valence electrons. But everybody else in group 8 will have 8 valence electrons. Question on that? All right, so let's take a look at beryllium, which is number 4. Again, it's going to have 4 electrons. We're going to start again up here, which is going to give us 1s2. That is now full. Again, we need to zigzag back around here to 2s, and we can put 2 more electrons there, and it would be 2s2. That is now 4 electrons up on top. We have 2 electrons in the first energy level, and we have 2 electrons here in the second energy level, and those would be the valence electrons for beryllium. If you look at beryllium on the periodic table, that is group number 2, and that is the 2 valence electrons that we see right here. If we continue on with boron, which is number 5, again, starting up there on top, always start at the top and continue to zigzag here. Starting here, again, 1s1 coming around. Sorry, 1s2. Zigzagging back here, we could fill this guy up to 2s2. We're not done yet, right? If we count the top, that's only 4 electrons, which means we now zigzag back to this guy, which is going to take us to 2p. And we would go 2p1 in this case. Now, when we look at this, that's a grand total of 2, 2, and 1 up on top. That's 5 electrons. This is the p subshell, which means we could fill up the p subshell with another 5 electrons, right? Until it's completely full, we could get to 6. What does this mean for our valence electrons for boron? Well, this is on the first energy level. On the second energy level, we have these two right here. And this guy is also on the second energy level here. That's a grand total of 2, and 1 more gives us 3 valence electrons. And if you look at, again, boron, that is group number 3 on the periodic table. And again, that matches. And again, because those are both 2, the S and the P, they're both on the second energy level. They're both the highest in energy. That's where our 3 valence electrons come from. Why don't we continue on with carbon, which is 6. Again, coming back to our top here, coming through here again, 1s2, zigzagging back around to this guy, coming through here, 2s2, again, zigzagging back this way. Now we can put another electron in there, 2p2. Again, if we count up the top, 2, 4, and 6 electrons. When we look at valence electrons here, these guys over here are the highest in energy level. We know that by this number here. 2 is bigger than 1. 1 means it's on n equals 1. 2 here means it's on n equals 2 in both of those. And that's a grand total of 2 and 4 electrons. And that would be 4 valence electrons for carbon, which is group number 4 on the periodic table. Any questions on that there so far? Okay, let's continue on. Might as well finish out the first 10 there. Nitrogen, which is 7. Again, starting up there on top and working our way and zigzagging, we're going to go 1s2. We're going to zigzag back to 2s2, and we're going to go back to 2p3 in this case. Again, we now have half filled. If we just look at the p subshell, just so you get an idea where we're at, we put an electron there, an electron there, an electron there. So you can see we have room for 1, 2, and 3 more electrons until that subshell is full. In terms of its valence electrons, again, we're looking for the ones in the highest number. So that's going to be this guy and this guy, which is going to encompass 2 and 3, which is 5 valence electrons there for nitrogen. And again, nitrogen being group number 5. Oxygen, which is 8. Again, 1s2, 2s2, 2p4 in this case. Again, putting our next electron here. And looking at the same idea, 2 and 2, which is our highest energy level. That 2 on top, and the 4 gives us 6 valence electrons for oxygen, which is group number 6. And fluorine, which is 9, gives us 1s2, 2s2, 2p5. Again, next electron going into here, scribbled. Same idea still. These guys are our highest here. Again, that is 7 electrons involved there, which is the 7 valence electrons. And to finish out the first 10 here for neon, 1s2, 2s2, 2p6. That is going to fill that last p orbital. And again, same idea. We still have our highest energy levels here, 2 there and 6 there gives us 8 valence electrons. And again, if you look at neon, it is group number 8. Question on how to write that electron configurations there. All right, so why don't you try one? Why don't you do... let's do, why don't you do calcium, which is 20? Why don't you write the electron configuration for calcium, which has 20 protons and 20 electrons. So take a moment and see what you come up with. Got multiple colors coming through. Well, we'll go purple. We can see it. So again, we're going to start up on top and follow that zigzag way. So that is going to be 1s2. That's going to be 2s2. That's going to be 2p6. If you're not sure, you can count the top numbers there, and we are at a grand total of 10 so far. That means we are done with the 2p. We then need to continue on to the 3s, 2. We're done with the 3s. We need to zigzag back around to our 3p next. So our 3p would come next. We could put 6 of them in there. And at this point, if we count up the top, we're at 18, which is close. We then need to go one more to our 4s2. Again, counting up the top there, you should end up with 20 in this particular case. Any questions on that? Now, if we look at this configuration and we look at it up to here, we count the top, that is 2, 4, 10, 12, and 18 electrons. If I look on the periodic table, number 18 is argon. I could put argon in brackets and continue on with the configuration. And this is what is sometimes referred to as noble gas configuration, right in it, which means inside the bracket should go a noble gas, sort of a shorthand, where you put the noble gas that comes right before the element, and then you continue on with the electron configuration. So for example, if I looked at magnesium, which is 12, I could write 1s2, 2s2, 2p6, 3s2. If I take this part of the configuration, that is 10 electrons, which means 10 electrons is neon, which is a noble gas, and I could write 3s2. So that's another way, sort of a shorthand way that sometimes electron configuration is written. Question on how to write electron configuration or figure out valence electrons from electron configuration. This is the way I would like you to write electron configuration for me. I then know in your book and also your lab notebook or lab book, she does that weird just kind of numbers. Again, don't do that for me like that. Do it like we just talked about here. I think is a little bit more understandable as well. Let's just talk about a couple more things here to finish up, which hopefully will answer some of the questions I think some people were asking. Let me see if I can find that here. There it is. So earlier, somebody was asking where maybe the D block is, where those type of things. You could actually count off electron configuration from the periodic table if you kind of know what you're doing. And actually, you know what? I'm going to grab one that's maybe a better one to kind of do it with here. But let me see here. There it is. Let me go back to those periodic tables we had earlier. Probably be a little bit better. Maybe. Okay. So if we look at the sort of the periodic table here, we can actually count off electron configuration. What can I do here? I think I can erase all these guys, erase all the ink on this screen. Perfect. Now I actually got something fresh. So if we look at the periodic table, there's our group numbers and there's also our period numbers. So these period numbers represent that n number. That's n equals 1. That's like n equals 2, n equals 3, n equals 4, n equals 5, n equals 6, and n equals 7. So when we look at the periodic table, the first two groups, group 1 and 2, that is the S block because it could hold 2 electrons, right? 1 and 2 electrons. The P block is from group 3 to 8. That's the P block. And P could hold 6 electrons, right? 1, 2, 3, 4, 5, and 6. The D block is actually your transition metals. If you remember, D block could hold 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Your F block are those 2 rows on the bottom, if you remember. It holds 14. I won't count it, but if you go all the way across, there's 14 boxes. So you literally can count electron configuration off of the periodic table just by kind of following them. I personally would not recommend doing that because there are some places where it could kind of go bad for you if you don't know what you're doing. But just to show you how it sort of would work, let's say we were going to do magnesium like we just did the configuration for. So magnesium, which is 12, right? We would start here and go across to helium. That would be and signify 1s2. We then would come here. That is now 2s2. We would come to the other side, which is still 2. This would be 2p, 1, 2, 3, 4, 5, 6. 2p6. Then we would come here. That is 3. This is now the s block. 3s2 would be the configuration. So you can count off an electron configuration. The problem is, and we'll talk a little bit more about it next time, but the problem is when we get to here, which is 4, this is 4s. And if you remember, what comes after 4s on our zigzag guy is 3d. So right here is actually 3d. This would be 4d. This would be 5d. This would be 6d. It is 1 behind the period number. So if you look over here, this is F. F starts on the 4th energy level. This would be 4F and 5F. And they should go right here, if you remember. Actually, right here. Sorry. Right there is where they should go. And that's number 6. This guy is actually 2 behind the period number. 2 behind. So if you don't know really what you're doing, you might end up with the wrong sort of way, 1 behind the period number. So I would highly recommend using the zigzag guy like we talked about. You will never go wrong with that. But in a pinch, if you want, you can kind of count it off the periodic table if you know what's going on. There are a couple of exceptions we'll talk about next time. Chromium and copper are some exceptions to what the normal electron configuration is. And I know I'm pretty much done here, but just let me just also make sure I answer everybody's question again. The valence electrons, like we did here, if we looked at magnesium, magnesium gets to here, which is the 3rd energy level. It would have 2 valence electrons, which again matches its group number. So everybody in the representative groups, group 1 has 1 valence electron, group 2 has 2 valence electrons, 3 valence electrons, 4, 5 valence electrons, 6, 7, and 8 valence electrons. Helium again only has 2, so it can't have 8, but everybody else